do reserve some attention for our next speaker. Jan, the hard act to follow. Sure, but Jan will do that. He can. Algebraic reasoning over relational structures. Please, Jan.
Okay, so hello. Just something brief about me. I'm doing a PhD at Masaryk University in Czech Republic, and I will tell you something about the collaboration with Stefan, Milius, and Henning Urbat from Friedrich Alexander University in Germany. Okay, so in the study of semantics, it often happens that there's an interaction between algebraic features and relational features. An important result when studying algebraic structures is Birkhoff's variety theorem, which I will very briefly recall. And so some examples of relational features are order, distance, and generalized distance. Does it point? Okay, I see. Thanks. Yeah, so some examples are order, distance, and generalized distance, and these correspond to ordered algebras of Bloom, quantitative algebras of Mardar, Parangaden, and Plotkin, and the recent generalized quantitative algebras of Meosarkis and Vignudeli. And what we do is that we provide an intuitive common generalization of those, and also obtain some new results. For example, a variety theorem for this last example is new. So here's just a very brief reminder of the classical case of Birkhoff. So we have some set, and on it we have some operations. Then we can talk about equations. So for example, this is an associativity equation, and classes of algebras that can be described by equations are called varieties. Some examples are semigroups, groups, or vector spaces. A non-example are fields. And the easiest way to see that this is a non-example is that it's not closed under products. And now the Birkhoff's variety theorem, it classifies these varieties. So when a class can be characterized by equations via closure properties under taking some constructions, so products, subalgebras, and quotients. And just to clarify some terminology, by quotient, I mean a surjective homomorphism, and being closed under it means that it is closed under taking images of quotients. Images under quotients, I mean. So sometimes, as I mentioned, it makes sense to consider relational features on top of these algebraic features and to have them compatible with each other. And on the side of equations, there are some choices one can make when choosing what kind of equations to consider, but a very reasonable choice are so-called C-clustered equations. So for ordered algebras, they can have two forms, either this first form or the second form. So now the equations are some kind of a deduction. For quantitative algebras, they can have this form. And for generalized quantitative algebras, they can have one of these two forms. The reason that it needs to have one of these two forms is that in the generalized case, one cannot identify equality with distance 0. And this C in C clusteredness, it's a parameter that classifies a certain connectedness condition on this left-hand side of the reduction. I will tell you more about this later in detail. So now the setting that we will be working in. So we will have a relational signature S, arities are natural numbers, and an S structure is a relational structure over this signature, so a set equipped with relations. Then morphisms are maps that preserve relations. And there's also a notion of reflecting relations, and something that we will use is an embedding. It's an injective map that both preserves and reflects relations. By STRS, we will denote these structures and the morphisms between them. So the ones that reflect, the ones that preserve the relations. And we will be considering classes that satisfy some universal infinitary Horn clauses. So they can have one of these two forms, deductions like this. And here's what satisfaction of these deductions means. So it's an implication like this for each assignment of variables in X but by values in A. So it's an implication like this in both cases. And we will fix, as I hinted before, this class C, and those will be the structures that satisfy some fixed set of these infinitary Horn clauses. So the leading example that motivated us are these generalized quantitative algebras. So first for this, one needs these generalized metric spaces. And it's a very simple idea. So what one does is that one takes these 5 axioms. The four first ones are the usual ones for metric spaces. And then just considers a fixed subset of these axioms. So for example, it can be an empty subset, or it can be subset containing all of these axioms, or just the first one. But we fix some subset like that, and we denote it XGM. And then a generalized metric space is just a kind of a distance like that, a fuzzy relation subject to these axioms. So these are the generalized metric spaces introduced by Milius et al. To have these generalized quantitative algebras. A map is, as usual, a non-expansive map, so it satisfies this inequality. And by GMAT, we will denote these generalized metric spaces and non-expansive maps. And note that this GMAT is parametric in this XGM in this fixed subset of axioms. So one can regard generalized metric spaces as a relational structure. So these first 5 axioms, they correspond to the 5 axioms from the previous slide. And then to really get a bijection, one also needs to add this upwards closure property and Archimedean property. And then by these axioms, one can describe these generalized metric spaces. So this C, this class that satisfies this fixed subset of axioms, if we consider this subset, then it becomes GMAT. Now, here are some simpler examples. So a very simple one, category of sets and functions. So it's just empty signature and empty set of axioms. And both sets, so it's signature containing one binary relation, and then these 3 simple axioms that everyone knows. So that's one way this generalized quantitative algebra stuff is generalized. The other direction in which this generalization of Milius et al. Goes is that they consider liftings, and in particular lifted signatures. So a lifting, it's simply a lifting of some functor from set to structures. So in this picture, G is a lifting of F. And then a lifted signature, it's an algebraic signature such that for each operation symbol, we have a lifting of this product functor, where n is the arity of the operation symbol. And perhaps to clarify a few things, we will be considering arbitrary these arities, so arbitrary cardinal numbers, and also some notation. So the lifting that takes some a, and it returns some relational structure. So it must be on an, since it is a lifting of this functor. And then the relations, we will denote them like this. So here are just some assumptions. We fix a lifted signature. Also a technical assumption, we will assume that liftings preserve embeddings. And also we will fix kappa such that each arity is below kappa. Each operational arity. So now what is a sigma hat algebra? So algebra for this lifted signature. It's first of all a relational structure that comes also equipped with these operations that lie in structures as structures, so that they preserve relations. And also here we have this lifted domain. A morphism is then simply a morphism of S structures and also an algebraic homomorphism, so it preserves operations. So just notation, these are the algebras for a lifted signature. And if we add this C here, I remind you that C are these relational structures satisfying a fixed subset of axioms of infinitary Horn clauses. Then we mean sigma hat algebras over C, which means the ones that satisfy these axioms in the fixed set of axioms. So some examples of this, because it might seem a bit. Okay, so some example. So a very simple lifting is a discrete lifting. So it equips an with empty relations. So there aren't any relational conditions on operations. Another more useful one is a product lifting. So it takes it to the product component-wise structure. So then the operation is relation preserving with respect to this component-wise structure, which I reminded here what this product structure is. So it's just on components. Meo et al. Considered, for example, these two liftings that come that are motivated by quantitative term rewriting and machine learning. So the first one is Lipschitz lifting, for which one obtains that the operations are alpha Lipschitz maps with respect to the product metric, and then the Lukashik-Karmovsky lifting, which captures non-expansivity of operations with respect to the Lukashik-Karmovsky distance. And in this example, both of these directions of the generalization and of these generalized quantitative algebras are important, because the Meo et al. Notice that one needs to, first of all, it's not a metric space, it's just a diffuse metric space. So some of the axioms of the metric space don't hold. And also for the usual product structure. It's not non-expansive, but by considering lifted signatures, one can get it non-expansive. And for posets, then there's again the discrete lifting and product lifting. The product lifting, it leads to monotone operations, and these are the standard algebras that were studied by Bloom. And then one can also combine these two together, and in some coordinates take it to be the discrete lifting, and in some coordinates take it to be the product lifting. And there's also, it's possible to do such stuff with lifting, so they provide quite a lot of flexibility in terms of what kind of relation preservingness to consider. So now we have the setting, and I will be getting to the variety theorem. So an important notion is C-reflexiveness. So it means that if we have something of cardinality less than C in the codomain, then we have something in the domain such that this original morphism can be restricted to an isomorphism like this. Isomorphism here corresponds to a bijective embedding. If it is surjective, then we call it a quotient, so C-reflexive quotient. And also for algebras, we cannot talk about C-reflexiveness also for maps of algebras by considering the underlying relational structures. So now a C-clustered equation is a deduction of one of these two forms. So you can see that it generalizes these C-clustered equations that were on one of the first slides. And what I will say here is this C-clusteredness condition. So C is some parameter, and what the C-clusteredness condition means that we can divide X into these disjoint XJs. Each of them is of cardinality less than C. And on the left-hand side, for each I, we get all the arguments of the relation that appear here, that they are in the same set XJ. So that's the C-clusteredness condition. And these are the C-clustered equations. So I just repeated them here, and satisfaction, it's as expected for every assignment of variables in X. We get an implication like this, and an implication like this. Here, since on the right-hand side there are terms, not just variables, one needs this extension to the term algebra. Yeah, and so here just that when instantiated to these examples, we already saw that the equations looked like this and like this. And for ordinary metric spaces, they correspond to C-clustered equations introduced by Milius and Urbat. They are quite closely connected to C-basic equations of Mardar, Panangaden, and Plotkin. So just some terminology. C variety is a class of these algebras for lifted signatures over C that is axiomatizable by some C-clustered equations. And then we obtained this variety theorem that a class of such algebras is a C variety if and only if it is closed under C-reflexive quotient. So these are the ones from the few previous slides. And also subalgebras and products. So these two are the usual ones, and then these are the kind of special ones. So for pose sets and C equal to 2, and the product lifting, so this corresponds to monotone operations, we obtain the classical variety theorem of Bloom for ordered algebras. And for all other choices of C and other choices of liftings, this leads to a new family of variety theorems. For metric spaces, this leads to a refinement of the variety theorem of Mardar et al., where we have these C clustered equations instead of C basic equations. And for generalized quantitative algebras, it leads to a new variety theorem. So just a very brief idea of the proof. So the idea is to use an abstract variety theorem that Milius and Urbat already had. So we fix a category A, a proper factorization system on it, so you can think of this as some kind of refined monomorphisms, refined epimorphisms and refined monomorphisms, a subcategory, a full subcategory, and some class of objects. This then leads to this class EX, which is defined via projectivity. So I'm going just very briefly through this. It's not important to have all the details. And then an EX quotient is a quotient from this class. And the importance of this is that in our examples, this will be precisely the C reflexive quotients, this class EX. An abstract equation is a morphism in E going from something in this class of objects X and into this full subcategory. And satisfaction is simply through factorization through E, like this. And with these notions of abstract equations and abstract satisfaction, one can have then abstract variety, and it's something axiomatizable by abstract equations. So class of objects in A0 is an abstract variety if it is axiomatizable like this. And now here's the abstract variety theorem. So there are some technical assumptions such as eco-well-poweredness and so on. And then under these technical assumptions, for every class V of objects in A0, one gets that it is an abstract variety if and only if it is closed under EX quotients, so quotients lying in EX, subobjects, and products. And these EX quotients, they will correspond to C reflexive quotients in our setting. So the classical Birkhoff theorem, A and A0 are the same. EM are surjective injective, and this X are all three-term algebras. And EX is simply all the surjective maps. In our case, it's a bit more distinguished, these things. So this A and A0, they are not the same anymore. This A0 are the ones are the algebras over C, and A are all the algebras. Here we get surjections and embeddings. And this X, they are again free-term algebras. I skipped a lot of details. It's quite technical, these free-term algebras in this lifted setting over C clustered structures. And then EX are the C reflexive quotient. So in this way, this abstract variety theorem can be used to a large degree to obtain our theorem, but there's still quite a lot of details that one needs to do to really obtain the theorem. So one more thing that we obtain is an exactness property. So yes, okay. In the classical case, there's a bijection between surjective homomorphisms. By classical case, I mean the Birkhoff's case. So bijection between surjective homomorphisms and congruency relations. So those are equivalence relations respected by operations. And one other result that we obtained is an exactness property in our setting. So for these lifted signatures over relational structures. So all the details aren't important here, but what's important is that we have a congruence as usual, and then we also have a refining structure. So it's it's this R prime that refines this R, and what's important is this first axiom. So by C prime, we mean the structures that satisfy the axioms where we omit the axioms that have equality on the right hand side. So, for example, in the metric space, this would correspond. One would get pseudometric spaces because one would drop the positivity axiom. That's the only axiom that has equality on the right hand side. All the other axioms have relations there. And then it's also needs to extend it like this and then be compatible with the operations and liftings. And so what's important is that we need both a refining structure and a congruence to be able to get this exactness property, and they also need to be compatible in some way. So there's the way this refining structure and congruence that we need are compatible. And then when one has this, then there's a bijection between quotients and these compatible pairs of refining structures and congruences. There's also some technical assumption that the liftings need to preserve the quotients that both preserve and reflect relations. So under this technical assumption, then one has this exactness property. And so some conclusions and future work. So we were considering the C-clustered equations over relational structures. This generalizes a number of notions that I mentioned. The useful thing is the clear separation between the algebraic and relational aspects. When considering the metric cases or the posets, it can sometimes be quite obscure what's the separation between those two. And then some future stuff to do would be to have a relevant complete deduction system and a sound one, and also to try to characterize these equation theories by properties of free algebra monads. So this is the bibliography, and thank you for your attention.
Metric theories.
Uh-huh.
But I think they can be understood as enriched. Algebraic theories enriched in metrics.
Uh-huh.
Is there some sense of enriched attributes?
I don't have it written down or checked in detail, but it's something that I thought about, and I believe it should be, because it's also for the ordered algebras, it's enriched in posets, and I think that these both cases can also be unified by relational structures like this.
So what would you enrich?
In a relational structure.
So maybe it's an enriched event theory.
Yeah, that might be the case.
Can you explain relating second example? Process as when you choose some instances where you take the max community when you don't way an example or
it's just an example to show that one has this flexibility on the domain thanks to these liftings. And in the paper there are a few more examples like this.
Okay, well, let's thank our speaker again.